Hey everyone, and welcome. Today we're diving into a Leetcode problem called minimum equal sum of two arrays after replacing zeros. Sounds a bit like a mouthful, right? But don't worry, we'll break it down step by step and make it super clear. Our goal is to understand the problem and then figure out an efficient way to solve it. Ready? Let's go. So here's the gist. We get two lists of numbers. Let's call them nums1 and nums2. These lists can have positive numbers and also zeros. Our job is to change every single zero in both lists into a positive whole number, so 1, or 2, or 3, and so on. After we've replaced all the zeros, we want the sum of all numbers in nums1 to be exactly equal to the sum of all numbers in nums2. And, here's the catch, we want this equal sum to be the smallest possible sum we can achieve. If it's impossible to make their sums equal under these rules, we should just say so by returning -1. Simple enough? Let's look at an example. Imagine nums1 is 3, 2, 0, 1, 0 and nums2 is 6, 5, 0. First, let's see what we have. In nums1, the numbers that aren't 0 add up to 6, 3 plus 2 plus 1. And there are two zeros. In nums2, the non-zeros add up to 11, 6 plus 5. And there's 1 0. The problem says we can make them both sum to 12. How? For nums1, we could change the two zeros to, say, 2 and 4. Their sum is 6. Add that to the original 6, and we get 12. For nums2, we change its 1 0 to a 1. Add that to the original 11, and we also get 12. So 12 is an equal sum, and it turns out it's the smallest we can get. Okay, here's another one. Nums1 is 2 0 2 0, and nums2 is 1 4. For nums1, the non-zeros add up to 4, 2 plus 2. It has two zeros. For nums2, the non-zeros add up to 5, 1 plus 4, and it has no zeros. This is interesting. If nums2 has no zeros, its sum is fixed. It's just 5, period. So for the sums to be equal, nums1 must also sum to 5. But wait, nums1 has those two zeros. To make the sum as small as possible, we have to replace each zero with at least 1. So the smallest sum nums1 can possibly have is its current 4, plus 1 for the first 0, plus 1 for the second 0, which is 6. Or, the smallest nums1 can be is 6, but nums2 is 5. We can't make them equal, so the answer here is -1. So what's our strategy here? We want the minimum equal sum. When we replace a 0, we have to use a positive integer. What's the smallest positive integer? It's 1, right? So if we want to keep the sum of an array as small as possible after replacing its zeros, it makes sense to change every 0 into a 1. This gives us a sort of base minimum sum for each array. Let's formalize that. For nums1, we can calculate the sum of all its numbers that aren't 0. Then, we count how many zeros it has. If we change each of those zeros to a 1, the total sum would be sum of non-zeros plus count of zeros. Let's call this its potential minimum sum 1. We do the exact same thing for nums2. Find the sum of its non-zeros, count its zeros, and calculate its potential minimum sum 2. These values tell us the absolute smallest sum each array could possibly have if it has zeros that need replacing. Now if we want both arrays to have an equal sum, and we want that sum to be as small as possible, well, the final sum for nums1 can't be smaller than its potential underscore sum 1. And the final sum for nums2 can't be smaller than its potential underscore sum 2. So the equal sum we're aiming for must be at least as big as both of these. This means the smallest target sum we could hope for is the larger of potential underscore sum 1 and potential underscore sum 2. But remember that tricky case from example 2. What if one array, say nums1, has no zeros? Its sum is just its sum. It's fixed. In this situation, nums2 must end up with that same fixed sum. If nums2 can't reach that sum, maybe its own potential underscore sum 2 is already too big, or too small. Even if it has zeros it can adjust. Then, it's impossible. This leads us to the conditions for when it's impossible. Let's say nums1 has no zeros. Its sum is fixed. Let's call it fixed sum 1. Now, nums2 needs to achieve this fixed sum 1. The smallest nums2 can possibly be is its potential underscore sum 2, which is its sum of non-zeros plus count of its zeros. If fixed sum 1 is actually smaller than this potential underscore sum 2, then nums2 can never get its sum down to fixed sum 1. Impossible, so we return -1. Symmetrically, If nums2 has no zeros, its sum is fixed sum2. If this fixed sum2 is smaller than what nums1 can achieve at minimum, its potential underscore sum1, then again, it's impossible. -1 it is. If neither of these fixed sum is too small situations happens, then it turns out a solution is always possible. So, if we've passed those impossibility checks, what's the answer? It's surprisingly simple. First, we calculate the sum of non-zero numbers for nums1, let's call it actual underscore sum1, and count its zeros, num underscore zeros 1. We do the same for nums2, actual underscore sum2, and num underscore zeros 2. The minimum equal sum will be the larger value out of these two. 1. Actual underscore sum 1 plus num underscore zeros 1. 2. Actual underscore sum 2 plus num underscore zeros 2. We just take the maximum of these two values. This works because actual underscore sum x plus num underscore zeros x effectively gives us the target sum for array x. If array x has zeros, this is its minimum possible sum. All zeros become 1. If array x has no zeros, then num underscore zeros x is 0, so this value is just actual underscore sum x, its fixed sum. The impossibility checks we did earlier ensure that if one sum is fixed, the other array can achieve that sum. And if both have zeros, they can both achieve the larger of their minimums. Cool, huh? Alright, here's the Python code for this logic. It might look like a bit, but we'll walk through the key parts. Don't worry, it's simpler than it seems. First up, these two blocks of code are pretty straightforward. The first loop goes through nums1. We're keeping two running totals. One for the sum of all the numbers that aren't 0, we're calling that S1. And another for just counting how many zeros we find, that's Z1. The second loop does exactly the same thing, but for nums2, calculating S2 and Z2. So after these loops, we know the sum of existing numbers and the count of zeros for both arrays. Next, we calculate these candidate underscore S1 and candidate underscore S2 values. Candidate underscore S1 is simply the sum of non-zeros in nums1, S1, plus the number of zeros in nums1, Z1. This represents the sum nums1 would have if all its zeros were replaced by 1. If nums1 had no zeros, Z1 is 0, then candidate underscore S1 is just S1, its actual sum. Same logic applies to candidate underscore S2 for the second array. These are our potential minimum sums we talked about. Now for those crucial impossibility checks. The first if statement looks at nums1. It asks, does nums1 have 0 zeros? That's Z1 equals 0. If yes, its sum is fixed at S1. Then it checks, is this fixed sum S1 less than the minimum sum nums2 can achieve, candidate underscore S2? If both are true, then poor nums2 can't shrink enough to match nums1's fixed sum. So, we return -1. The second if statement is the mirror image for nums2. If nums2 has no zeros, its sum is fixed at S2, and this sum is less than what nums1 can achieve at minimum, candidate underscore S1, then it's also impossible. Return -1. Finally, if we've gotten past those if statements, it means a solution is possible. And the answer is simply the larger of our two candidate sums, max, candidate underscore S1, candidate underscore S2. As we discussed, this correctly handles all cases. Whether one array has a fixed sum and the other can match it, or both have zeros and can be adjusted to meet at the higher of their minimums. So how efficient is this approach? For time, we basically iterate through nums1 once and then through nums2 once. If nums1 has n elements and nums2 has m elements, the time taken is proportional to n plus m. We call this big O of n plus m, or order n plus m time. That's pretty fast. And for space, we're just using a few variables to store sums and counts, S1, Z1, S2, Z2, etc. This doesn't depend on the size of the input arrays, so the space complexity is big O of 1, or order 1, which means constant space. Very memory efficient. Alright, let's recap the main points. The core idea is that to get the minimum sum for an array when replacing zeros, we should change each zero to a 1. This gives us a potential minimum sum for that array. We have to be careful if an array has no zeros, because its sum is then fixed. If this fixed sum is smaller than what the other array can possibly achieve, even with all its zeros as 1s, then it's impossible. But if it is possible, the minimum equal sum we're looking for is simply the larger of the two arrays' potential minimum sums. And that's how we solve the minimum equals sum problem. I hope this explanation made sense and was helpful. If it did, feel free to hit that like button, subscribe for more Leetcode breakdowns, or drop a comment if you have any questions or other ways to tackle this. And hey, if you're feeling extra generous, the Boba Fund is always open. Keep practicing, keep coding, and I'll catch you in the next one.